Now, there are a couple applications and some interesting natural occurrences that happen that are related to polarization. Um, the first sort of application that I'm going to talk about is an LCD screen, liquid crystal display. And the way this works, LCD is an interesting thing. You have unpolarized light coming in, and most sources of light that we have around are unpolarized. Light from the sun is unpolarized. Light from our light bulbs is generally unpolarized. And so there's this light coming in from the environment that is unpolarized. Okay. Now the LCD, on an LCD screen, there's a polarizer, and I believe it's typically vertically polarized. Yes, it's typically vertically polarized. So the light that enters into the actual screen, and this is like the calculator screen is like this. The light that enters into the display, it becomes vertically polarized. Now, there are liquid crystals then. There's this layer of liquid crystals, and these liquid crystals can be oriented in one direction or another, and when you run a current through the liquid crystal by applying a voltage across it, it causes the polarization to rotate. So if the polarization is this way, then all of this vertically polarized light just passes through the LCD also, and it reflects back off, the back part of the display, and that's what the calculator looks like right now. So this vertical polarized light passes through the screen, and it hits the back of the display and reflects back, and we see this sort of, I don't know what you would call that color. It's a little bit greenish maybe, but yeah, so we see that reflecting back. Now, if we run a voltage across this will change its orientation to be horizontal. And that, if I turn it on, creates this region. It's applying a voltage and then removing it to create this blinking cursor. If I start typing numbers, that means there's some voltage being applied that's creating a horizontal polarization in the LCD in the shape of this 5, which means that the ambient light, in the room is being blocked by this region that says 5, because we've got this, vertical and horizontal together that blocks light. And that's what creates the display on something like a calculator or a Kindle or anything like that. I thought that's kind of interesting. Another use of this is in chemistry. Certain compounds do something kind of similar to the LCDs in that when light is kind of fired through them, it tends to certain compounds tend to cause that light to be polarized. And so if you've got a solution with some amount of this compound and you throw a beam of polarized light at it, the amount of light that's transmitted can tell you the concentration of your solution. It can tell you how much of that compound is in there, because the amount of compound in the solution changes the polarization of the solution, and therefore how much light passes through. Another natural phenomenon that has to do with polarization is scattering. If a molecule gets hit by a beam of light, it kind of absorbs and then re-emits some of that light based on how the electrons and whatnot have moved. Now recall from when I talked about antennae initially that there's only radiation in the direction perpendicular to the accelerating charges. Okay, so if we take a simple example, say we've got some kind of molecule here, and it's hit with a vertically polarized beam of light. Okay, let's say this is going in this way, it's hit by this vertically polarized beam of light. That's going to cause, pieces of this molecule to oscillate in the vertical direction, which means that if you're looking at it, from anywhere, from the left, the right, or into the page or out of the page, you'll be able to see it radiating polarized light. It'll radiate polarized light here. It'll radiate polarized light, at some point out of the page or into the page, and you'll be able to see that because these particles in the atom are oscillating this vertical direction. If you go below it, now if you're looking at it like from down here, then you're not going to see anything because you're looking down. Your line of sight is the same direction as the acceleration of the electrons or whatever in this molecule, and so over at a point below it, you see no radiation. Okay, so that's easier to think about. Now let's say we've got some unpolarized light coming in at our molecule, and it's moving this way, hits our molecule, and this guy starts oscillating about in all directions. However, if this is moving to the right, this is difficult to visualize, so I'll probably try to re-explain it in class. But anyway, let's say this is moving to the right and it's unpolarized. Okay, that means that the E field is oriented in all different directions. But if it's moving to the right, this wouldn't be an accurate way to draw it. Really, if it's moving to the right, it would be like a side view here. It would be it's radiating in all directions in the plane of the page, but there is no polarization going into the page or out of the page, if that makes sense, hopefully. So then when it's hit by this, if you look at it from here or here, you're going to see unpolarized light. Okay, and it's polarized all over the place over here, but this polarization is actually in the plane of the page, or is oriented. So if we're actually looking at it, it would look something like this from the side view, because it's oriented, it could be this way, or it could be into the page, out of the page, or any sort of, angle. It could be oriented this way, or any sort of angle along this rotational whatever. So it's oriented any of these directions. So if you look at it from over here, you can see it vertical, or you could see it any of these directions. Okay, but now let's think of what happens if you, again, are, say, down below it. Okay, it's oriented all in these directions, so this thing could oscillate in any of these directions. Okay, well, if you're down here, the component into the page or out of the component of the oscillation into the page or out of page is what is perpendicular to you if you're down here. Whereas the component that's in the plane of the page is in the same direction as your line of sight. So down here, you're going to see light that is polarized, into the page or out of the page. And so, light scattering down here is then polarized in a particular direction, even though the incident light is unpolarized and the light here or here is totally unpolarized. And then at any point in between, it'd be kind of partially polarized. And that's tough to explain when I'm dealing with a 2D paper. So hopefully, I'll take a minute. I'll talk about that in class, and hopefully we can figure it out. Right. Now, this allows you, if you can sort of measure the polarization, this could allow you to figure out where the sunlight is coming from. And scientists think that some organisms use that polarization to navigate by figuring out where the direction of the sun is. Anyway, the diagram is in your book on page 894. There's a diagram that shows this better than I can on my 2D paper. and when I'm not good at drawing. Another fun fact is that the size of these molecules, if the size of these molecules is close to the wavelength of the light, things scatter more. And the size of the molecules in the atmosphere scatter blue light more, and that's actually why the sky appears to be blue if you're not looking directly at the sun. And that's also why, when you have a sunset, the sun appears red. It's because those blue wavelengths are being scattered off, in other directions other than that straight line between you and the sun, and so you see the redder wavelengths that pass straight through without being scattered as much. Now, a similar sort of thing happens when you've got sunlight reflecting off of a lake. So you've got this unpolarized light radiating out from the sun, and it's hitting the water of a lake or pond or whatever. And this polarization, so if you're on it in the usual way, but it's actually oriented, so that it's polarized, it's traveling away from the sun, and so it's polarized kind of all along that path. It's polarized like this way. There are beams in all the directions going along this sort of rotational orientation. So when it hits the molecules in the water, it'll cause them to oscillate in all of these kinds of directions. Okay? And again, only the ones that are coming out of the page make any difference to somebody standing on the shore over here. The ones that are, in the plane of the page are more or less perpendicular to the line of sight. Here, so this line of sight here, the ones that are important are the ones that are oriented in this direction, while this is oriented almost perpendicularly. So then the light coming off of this surface is more or less horizontally polarized. And that's why we have polarized sunglasses. These polarized sunglasses are vertically polarized. And that cuts down on glare reflecting off of water, or, it reflects off other cars and cars if you're driving on the road, stuff like that. So any sort of flat reflective surface reflects mostly polarized light, and so if you have these polarized sunglasses that are polarized vertically, it cuts down on that glare from the reflected light. So actually, if you have sunglasses and they're reasonably, if you have reasonably nice sunglasses, they're probably polarized. And if you're not sure, you can tell, if you just turn on your calculator, right? Remember I said that, or not your calculator, like if you're looking at your computer screen, it's an LCD display, and that LCD display is vertically polarized. And so if you have on your polarized sunglasses and you turn them sideways and look at your computer screen, if your sunglasses are polarized, then your screen will go dark, because then you have those the polarization of the light coming out of your screen is vertically polarized, and then you got a horizontally polarized, and you got your vertically polarized sunglasses, which means if you turn them on the side, they become horizontally polarized, and then your screen will go dark because you have that 90-degree polarization. That's an interesting thing to tell. If you have sunglasses, you can try that out at home. Yeah.